This is part 2 of the histogram analysis lecture. So I left off here saying that analysis of the histogram is fairly complex and it can get very detailed in all the readings that you might do. But we should know that the shape of the histogram stays fairly constant, constant for each part being exposed. Another way to say that is that it is anatomy specific. So a histogram might look a little bit different for a chest x-ray compared to a KUB, compared to an extremity. The computer will analyze the histogram with processing algorithms, compares it with a pre-established histogram that has already been set up, which is specific to the anatomic part being imaged. This is called histogram analysis. So for example, the shape of a histogram of a chest image on a large adult would look very much different from a knee histogram from a pediatric patient. So it's very important that we choose the correct anatomic region on the menu before exposing the patient. So here we have comparison of two different knee images. Both of these knees were taken at 75 kVp and 8 Mass. They were both taken at the same distance. One was processed under knee at the reader, while the other was processed under upper ribs at the reader. You can see that when we exposed the knee image, we ended up with an exposure index of 159. This is perfect because the normal should be anywhere between 150 and 250. However, when we processed the knee, again taken at the same technique, but processed under upper ribs, our exposure index dropped to 132. So what this is showing us is that we must select the correct body part, projection, position whenever we go to process our images, because it will affect the exposure index, which is linked to the histogram. The computer software has stored histograms or models, each having a shape characteristic of the selected part, region, and projection. So each exam that you take is going to have a stored histogram or a stored model that should be comparable to the image that you take. The stored histogram models have values of interest, or abbreviated VOI, that determines the range of the histogram data that should be included in the displayed image. So for example, these values of interest are going to vary between doing a chest x-ray and an extremity, because what values we need to generate those images are going to differ. So stated again, each image or each body part, each projection has its own histogram. Again, these histograms are stored in the computer and get used as comparison in creating your exposed image. So if you remember, each exam has a typical histogram that's stored in the computer for comparison. The computer is then going to use a lookup table, or LUT, for image processing. The lookup table contains a standard degree of contrast for that image, speed, and latitude for a given exam. There is a lookup table for every anatomical part. Image processing will give us proper grayscale, resulting in consistent looking images. The histogram that's being created based on the lookup table for the exam is going to give us consistent images from technologist to technologist, from room to room. So the radiologist is always looking at consistent looking images. So lookup tables can be graphed as plotting the original values ranging from 0 to 255 on the horizontal axis, and the values, on the new values on the vertical axis. We can change the contrast of our image by changing the slope of the graph. Brightness or density can be increased or decreased by moving the line up or down on the y-axis. And basically what this is saying is that you can change the window level and you can change the window width by changing the histogram. So here is just kind of an explanation of that. This picture comes out of your textbook. We can change the window level by moving this line up or down. That will change the brightness. We can change the window width by adjusting these numbers, and a non-enhanced, unprocessed image can be changed, and you can see that in gray here, which changes the contrast of our image. So basically, if the histogram from your exam is not the same as what the computer thinks it should be based on the anatomy you selected, it's going to manipulate that data to try to make it look the same as what it has stored for a basic exam or projection. Some things do have to be correct for all of this to fall into place and have a good image. So the lookup table data has to be correct. Of course, your positioning has to be correct, centered to the image receptor. Collimation needs to be equal and centered, and of course, correct technique. Appropriate part and projection selected by you at the reader has to be in place prior to processing. You might also have to select things such as the orientation of your image receptor. Was it portrait? Was it landscape? Patient position. Was the patient AP for a chest x-ray? Were they PA? Was this a pediatric patient? Etc. Then true patient information is determined. The information then is automatically rescaled to stabilize the density and contrast. I can't stress to you enough that this is a compensatory tool. It can compensate for slight variations in part thickness and maybe small to moderate technical errors in KVP and mass. So automatic rescaling means images are produced with uniform, consistent brightness and contrast, regardless of the amount of exposure used to acquire the image. This can be dangerous because we can then rely on the computer too much to fix our images. So the computer rescales the image based on the comparison of the histograms, which is actually a process of mapping the grayscale to the volume of interest to present a specific display of brightness. Now, each manufacturer is going to use a little bit different naming or way to manufacture this algorithm. So Fuji uses something called MFP, Kodak uses something called tone scaling, and Agfa uses something called Musica. This will be talked about a little bit more in the third segment of this PowerPoint for Chapter 3. So this picture is just showing us that regardless of the amount of exposure that you used, images are going to appear with consistent brightness and contrast because of automatic rescaling. So the image here in the middle is of optimum quality. It was good exposure. The image on the right here was made with high exposure. The image on the left here was made with low exposure. But you can see that they look fairly consistent from one to the next. The difference in the image here on the left, I will point out, has noise, also known as quantum model, because of the low amount of exposure. However, the density, the contrast on all three of these is consistent because of automatic rescaling, which uses a stored or model lookup table and histogram to compare your image with. Now, problems can occur with automatic rescaling if you don't select the correct anatomy, if you use too much or too little exposure. If you choose the incorrect anatomy prior to processing, the image won't process correctly in regards to density, contrast, or brightness. However, most images allow you to reprocess the image without having to repeat the exam. Here is an example of a pediatric chest, and it was processed under an adult chest selection, and you can see it has very poor quality. Not to add, they should have collimated. But regardless, I don't have to repeat this patient. I simply can reprocess it under a pediatric AP chest image. Here's another example. We have a knee, lateral knee taken. This one looks pretty darn good as far as density and contrast is concerned. On the right, however, we have an image with very poor quality. The contrast is poor because it was processed under a chest PA. And again, I told you that when the system looks for density values to use to create the histogram, it's using those values based on the exam that you tell it that you're performing. So it used densities that were taken, but just altered those densities to try to make this image look like a PA chest x-ray. Again, if we have too little exposure, our image will have quantum model. This cannot be fixed. The image has to be repeated. If we use too much exposure, too high of mass, too high of kVp, we're going to lose out on contrast somewhat, and we could have a loss of the distinct edges of an image because we have more scatter, usually with higher kVp. So automatic rescaling should be no substitute for appropriate exposure factors. You must know your correct mass and kVp values in order for the histogram to be created correctly. We should never rely on the system to automatically rescale our images with proper density and contrast. As I've said 1,000 times, we can't put the cart before the horse. This can lead to something called dose creep, which we'll talk about later. But dose creep is essentially relying on the system, the computer, to fix your image through rescaling. And over time, this is going to result in you using higher than needed exposure values. Essentially, your doses that you use and give to patients are going to creep up over time. Secondly, there is very good validation for using technique charts. These should be used by technologists to determine that the appropriate signal-to-noise ratio is being used and is acceptable. Okay, this concludes segment 1 of Chapter 3 PowerPoint covering the histogram. I encourage you at this point to next go under Content and find the quiz that covers histogram. There's just a small amount of questions, and what it does is allow you to test your knowledge over these first 2 segments regarding histogram from Chapter 3. Please contact me at any time with any questions.